This is a recap of the distance formula, probably introduced after Pythagorean theorem. You're given a bunch of graphs here. You're introduced to the distance between what could be this point here and this final point here. We previously talked about Pythagorean theorem, but this activity will explore how we can find the distance between 2 points without even necessarily needing to draw the right triangle for Pythagorean theorem. Capiche? Sound good? So let's get into it. You're being given this example here. The Podunk High School drill team choreographs their dance moves. They lay out their positions on a grid. Grid is seen here. In one of their dances, they plan to make patterns holding long, wide ribbons that will span from one dancer in the middle. Seen here, we have this person in the middle, to 6 other dancers on the grid. Their pattern looks like the following. Gabriella will stand in the center. I've marked that off with X. Some dancers think that the ribbon from Gabriella G to C, so this segment from G to C, they're claiming that that will be shorter than the one from G to B. So in blue, I have G to B. In green, I have G to C. What do you think? Is that the case? Is GC less than GB? What do you think? Take a moment, think about it. So you could have said something like the following. They're correct. GB is on a diagonal. GB's length is greater than 5 and greater than 5, which is the length of GC. Capiche? So here we're being asked exactly how long each ribbon is from G to C. You can just count 1 unit, 2 units, 3 units, 4 units, 5 units. So this is 5 units. We found this because it's a horizontal line. We just counted the spaces. From G to B, though, how do you think we could get that? Well, if we draw this vertical line or altitude, does this now look like a right triangle with a side length of 4 and side length of 4? And a missing hypotenuse here that we're trying to find? Sure does. So we can get a hold of G to B. If we take care of that, square 4, square this other 4. Notice I'm squaring that twice, and this should equal our hypotenuse being squared. We could take the square root of all that. Eventually, if you simplify all this, this is going to claim that it is the square root of 16 and 16. So the square root of 32, which is approximately 5 and some change, which would make this definitely a lot bigger. So here we could say that the length of this is going to be square root of 32, or approximately 5, and maybe like 5.2. I don't know exactly, but GC in this case is not as long as G to B. So we have a new pattern seen here, and this is now asking if the previous ribbons we were using of 5, 5.2, approximately 5.2. So the previous pattern, if those were going to be long enough to go between B and C and the new pattern shown here. So we see B to C is now making, let's count, a right triangle of 2 for the base, 4 for this side. And then we could say that this is, well, we don't want to necessarily say that's C squared, but C is there, okay? So if we find B to C, we know that C squared should be equal to 4 squared plus 2 squared. We can then say that if we just take the square root of all this, C should be equal to square root of 20, which is definitely, what? Is this less than 5 and 5.2? What do you think? It's definitely less than the 5, which is less than 5.2. So the previous pattern would work. Yeah. So will the ribbons they used in the pattern previously be long enough? You could say yes, because the 5 was the length originally of G to C, and 5.2 was originally G to B. And these are all greater than square root of 20. If you're not convinced, use a calculator to get square root of 20. See you on the next one. So here we're trying to find that distance from L to M. We could definitely make a right triangle, no problem there. One of the legs is 3, the other leg is 2. L to M goes like that. We can find C. We take 3 squared, we add 2 squared, that should equal 3 squared, or sorry, C squared. We could then just take square roots of everything. If you ever need to use a calculator for this, please do so. But this should be the square root of 13 for C. So we know that square root of 13 units to go from L to M. Typical Pythagorean theorem problem. Now let's see how this gets amped up on the next slide. So we're now being asked to talk about the coordinates. Well, we know that L was this coordinate here of 5, 8. We also have the M coordinate, which is 8, 10. Got that. This is having us subtract the X coordinates. So let's take a look at this. So we said that 5, 8 was the point for L. 8, 10 was the point for M. So this is having us just subtract these X coordinates. So we said X of M was going to be 8. And if we want to deduct X of L, that's 5. So this should be equal to 3. Makes sense, right? And if we do the same thing for the Y coordinates, we don't really know why we're being asked to do this, but maybe we'll see something soon. This question here is asking, why are those answers the same as the legs of the triangle on the previous slide? Well, you could take note of just the X coordinate. Let's start there. Because didn't we say that our X coordinate for L was 5, but the X coordinate for M was 8? And we kind of got rid of this portion that wasn't used for all this, which would be pretty much getting rid of 5 units, leaving this sweet spot here of 3. That's kind of what we just did. We did the same thing for the Y coordinates. So let's see how we can use this to our advantage. So we just saw that we could take the difference between the X coordinates, and we're being asked to kind of do the same thing here, where we know that if we have this bottom leg, this is the same thing as if we were taking this X coordinate and deducting this X coordinate here of XA, which would give us this segment in blue. What about for the Y coordinate? Well, didn't we just take whatever this Y coordinate was and we deducted this Y coordinate, getting you YB minus YA? And isn't that what the leg could be rewritten as, even if we threw in numbers? So this is helpful now because we could use this instead of using Pythagorean theorem. We know this is a leg. We know this is a leg. So we could really just take the square root of those two being squared. And that would actually give us our distance in one shot. Where again, we take the differences of the X coordinates, difference of the Y coordinates. So notice this is just the difference of the X coordinates. This is just the difference of the Y coordinates. And again, we kind of treated this as if it was a leg of the triangle, which is not far-fetched. Look at it. We'll try this out in an example on this next slide. So we were saying, based off of the previous information, that we could get our new distance. So our distance can be equal to square root of our X coordinates being subtracted from each other and the difference of the y coordinates being subtracted from each other and squared. So I'm going to just follow through with this kind of the same way that I did on the others. So I'm going to call this point XA. I'm going to call this YA. And I'll actually clean it up so you can actually see it. So let's do this again. We've got XA, got YA, we got XB, YB. So we can just plug in all those numbers that are written. So I'm taking the square root of YB, which is 9. I'm deducting YA, which is 6. I'm squaring that. I'm then adding on XB, which is 7, and then deducting YA, which is 6. And I'm squaring that. And so what's cool is that if you just let the calculator do the work for you here, it's going to knock out what you need. But if you wanted to take this further by hand, 9 minus 6 is 3. You're squaring that. You're adding on 7 minus 6. Sorry, pump the brakes. These were the y coordinates. So this should be 7 minus 3. My bad. Easy fix, though. 7 minus 3, which is 4, being squared. This is really just the square root of 25. So our distance between these 2 points is actually 5. If you're not convinced, you could plot it out. But this is a pretty typical type of right triangle that comes up. 3, 4, 5. So that's distance formula. This helps us get there. Keep going with the other ones, though. So what's cool, again, is that if you have this formula written down, square root of your x coordinates deducting from each other, being squared, and adding on the y coordinates deducting from each other and being squared, you're pretty much home free. Just label away XA, YA, XB, YB, and go to town. So this would be 23 minus 11 being squared. You're adding on 16 minus 5 being squared. This is really just what? 12 squared plus 11 squared. You can let your calculator do the rest here, but that's your distance. So lo and behold, I didn't even need to graph this out. I didn't need to make a right triangle. I just labeled the points XA, YA, XB, YB, and went to town. I hope that this video was helpful. If you have any questions, holler, let me know, say something. Talk soon.